Welcome to another deep dive. Today, we're going to be exploring transformer models and how they're changing the game for natural language processing. Getting computers to actually understand human language.
It's more than just understanding words. It's about grasping the nuances, the context, even the emotion behind them.
Right, like teaching a computer to read between the lines. And we're going to dive into how you fine-tune these models for specific tasks. It's kind of like giving them specialized training. Think of it like this. We spoke with Jordan, an AI engineer who works with these models every day, and he broke it all down for us.
What I find fascinating is that this fine-tuning process isn't a one-and-done deal. It's this incredibly iterative process. Jordan outlined 5 key steps, starting with prepping the data.
Okay, so walk me through this. How does he get this data ready for the model?
Well, he starts by gathering the right data for the task. Then there's this process called tokenization, where the text is essentially broken down into smaller units, sort of like digital building blocks for the AI.
So it's like chopping a sentence into individual words or even parts of words. Makes sense. Then what?
That's when the real crafting begins. He has to design the prompts, which are essentially the instructions or questions we feed the model. This is where the human element really comes in. We're guiding the AI's learning experience.
It's like choosing the right textbook and study guide for a student. You don't want them just memorizing facts, you want them to understand the concepts.
Exactly. And then comes the selection of hyperparameters. These are like the knobs and dials that control how the model learns. This part can get pretty technical.
Technical how so? Give me an example.
For example, imagine you're adjusting the learning rate. Set it too high, and the model might miss subtle patterns in the data. Set it too low, and the training could take forever.
So it's a balancing act. So he's prepped the data, set the learning parameters, then what?
Then comes the fine-tuning itself, where the model is trained on the specific data. And this is where it gets really interesting because Jordan constantly monitors the model's progress using various metrics, including one called Perplexity.
I've heard that term before, but honestly, I'm a little fuzzy on what it means. Can you break it down for me?
Sure. Jordan described Perplexity as a measure of how well the model predicts the next word in a sequence. Think of it like the AI is playing a game of guess the next word.
Okay, so the lower the perplexity score, the better the model is doing. But what does that really tell us? How does it show if the model is truly learning or just memorizing?
Good question. A high perplexity score might indicate the model is just regurgitating phrases it's seen before, like someone who crammed facts for a test but doesn't really understand the material. On the other hand, a low perplexity score suggests the model is starting to grasp the underlying patterns in the language and can actually generalize to new unseen text.
So it's not just about getting the right answer, it's about understanding the why behind the answer.
Precisely. And one of the key innovations that allows these models to achieve this deeper level of understanding is a mechanism called self-attention.
Okay, self-attention. Honestly, that sounds a bit intimidating. What does that even mean?
It might sound complex, but the concept is actually quite elegant. Self-attention allows the model to analyze an entire sentence all at once, understanding how each word relates to every other word in the sentence.
So it's like reading a whole sentence simultaneously instead of one word at a time.
That's a great analogy. It's a huge leap from older approaches, where the model had to process language sequentially word by word. This parallel processing power is what gives transformers their ability to grasp context and nuance so effectively.
This is fascinating stuff. But all this complex processing must require a ton of computing power, right?
You're absolutely right. The computational demands of self-attention can be a real challenge, especially when you're dealing with very long chunks of text. But Jordan has developed some clever techniques to address this. He essentially creates shortcuts for the AI to take without sacrificing accuracy.
Shortcuts. I'm intrigued. Tell me more about these techniques.
He uses several approaches. One is called sparse attention, where the model focuses its attention on specific parts of the text rather than trying to process every single word. Another is segmented attention, where the text is divided into smaller chunks and the model keeps track of the context from previous segments.
So it's like reading a book chapter by chapter, but still remembering the overall plot. Smart.
Exactly. And finally, there's efficient attention, which involves some fancy math to make the calculations less computationally intensive.
So it's all about making the AI work smarter, not harder. I like it.
Exactly. But even with all this advanced processing power, we still have to account for something very basic, the order of words in a sentence.
You mean like how dog bites man is very different from man bites dog?
Precisely. And that's where positional encoding comes in. It's a way of telling the model where each word sits within the sentence so it doesn't get confused. There are two main approaches, sinusoidal and learned.
And which one does Jordan prefer?
Well, he says it depends on the situation. He described sinusoidal encoding as a general-purpose tool, something that works well in most cases. But learned encoding, he said, has the potential to be much more specific, like a tool, custom-built for a particular job.
So it's like using a Swiss Army knife versus having a specialized instrument crafted for a specific job. Interesting. And how does he decide which one to use?
That's where his expertise comes in. It's about understanding the nuances of the task and the data, and choosing the approach that's most likely to yield the best results.
It sounds like fine-tuning these models is a real blend of art and science. But wait, there's more, right? Didn't you mention something called multi-head attention?
Oh yes, that's another key innovation that allows these models to analyze text from multiple perspectives simultaneously. It's like having a team of experts, each focusing on a different aspect of the language.
So, like one expert might be looking at the grammar, while another focuses on the emotional tone.
Exactly. Jordan shared an example from a project he worked on where some of the attention heads in the model were picking up on emotional keywords, while others were more focused on sentence structure.
This is getting really deep. We're talking about AI that can understand not just the words themselves, but the subtle ways we use them to convey meaning and emotion.
And that brings us to an important point about how these models are evolving. They're not just getting better at understanding text, they're getting better at understanding the world that text represents.
Okay, I'm on the edge of my seat here. Tell me more about where these models are headed.
Well, Jordan is particularly excited about the potential of what he calls multimodal AI.
Multimodal AI, what's that all about?
It's about breaking down the barriers between different types of data. Imagine AI that can seamlessly integrate information from text, images, and even sounds.
So it's not just about understanding words anymore, it's about understanding the world those words represent. That opens up a whole new universe of possibilities.
Exactly. And that's where we're going next in our deep dive. We're going to explore this fascinating world of multimodal AI and what it means for the future of how we interact with technology, how we learn, how we create.
Stay tuned, folks, because things are about to get even more mind-blowing.
It does, doesn't it? But this is where the field is heading. We're moving beyond AI that can just read and write. Now we're talking about AI that can process information from images, videos, and audio just as effectively as it can process text.
So what does that look like in practice? What kind of real-world applications are we talking about?
Think about medical diagnoses. Imagine AI that can analyze not just medical records, but also X-rays, MRIs, and even the sound of a patient's heartbeat to detect subtle patterns that might indicate a problem.
Wow, that would be revolutionary for healthcare. What about other fields?
The possibilities are really endless. In education, imagine AI tutors that can tailor their teaching methods to individual students based not just on their test scores, but on their facial expressions and their tone of voice.
It's like the AI can sense whether a student is bored, confused, or excited, and adjust its approach accordingly. That's incredible.
And think about the impact on creative fields. Imagine AI collaborating with musicians to compose symphonies that evoke specific emotions, or working with artists to create paintings that capture the essence of a particular scene.
This is starting to sound like we're giving AI senses, like we're allowing it to experience the world more like humans do.
That's a great way to put it. And the thing is, we're already seeing early examples of this. Models like GPT-4 can handle both text and images, and vision transformers are specifically designed for image understanding.
So these aren't just theoretical concepts. This technology is already out there in the world.
It is, and it's advancing at an incredible pace. But as with any new technology, there are challenges to overcome.
Like what? What are some of the hurdles that researchers are facing with multimodal AI?
One of the biggest challenges is integrating these different data modalities effectively. Text, images, and sounds are all very different types of data, and getting an AI to understand how they relate to each other is incredibly complex.
So it's not just about teaching the AI to recognize a cat in a picture. It's about understanding how that image relates to the word cat, the sound of a cat meowing, and the concept of feline in general.
Exactly. And another challenge is ensuring that these models are robust and reliable. We don't want AI making medical diagnoses based on faulty data or composing music that's unintentionally offensive.
Right. So there's a lot of responsibility that comes with developing this technology.
Absolutely. But despite the challenges, the potential benefits of multimodal AI are so significant that it's definitely an area worth exploring. It could revolutionize how we learn, how we communicate, how we create, and how we solve problems.
You've certainly given us a lot to think about. It's clear that fine-tuning these transformer models is a complex and nuanced process.
It is. And it requires a deep understanding of both the technology and the data.
Speaking of data, we talked earlier about how Jordan preps and tokenizes the data before he even starts training the model. What are some of the key considerations there? What does he look for in the data itself?
Well, one of the most important things is ensuring that the data is high quality and relevant to the task at hand. If you're training a model to translate languages, for example, you need a massive data set of high-quality translations.
That makes sense. But wouldn't any large data set of translations do? What makes for high quality in this context?
You need translations that are accurate, consistent, and free from errors. And it's not just about the quantity of data, it's also about the diversity.
Diversity, how so?
You want to make sure your data represents a wide range of language styles, dialects, and cultural contexts. This helps prevent the model from developing biases and ensures that it can generalize to a wider range of inputs.
So if you trained a translation model on a data set that was entirely composed of formal academic writing, it might not do a very good job of translating casual conversations or slang.
Exactly. And the same principle applies to other tasks as well. If you're training a model to generate creative text formats like poems or code, you need to expose it to a wide variety of examples to spark its creativity.
This is all starting to sound like we're not just training models, we're educating them, we're shaping their worldview.
That's a really interesting way to think about it. And it highlights the fact that we have a responsibility to ensure that these models are trained on data that reflects the best of humanity, not the worst.
Right. We want AI that's fair, unbiased, and aligned with our values.
Exactly. And that brings us back to the importance of metrics like perplexity. It's not just about measuring how well the model performs on a technical level. It's about understanding how it's thinking, how it's interpreting the world, and how we can guide its development in a positive direction.
So perplexity is like a window into the AI's mind. It gives us a glimpse into its thought processes.
Precisely. And by carefully monitoring these metrics and making adjustments along the way, we can help ensure that these models are not just powerful, but also beneficial to society.
Okay, let's shift gears a bit and talk about something we touched on earlier, positional encoding. You mentioned that it's a way of telling the model where each word sits in a sentence. Can you unpack that a bit more? Why is that so important?
Sure. Imagine you're trying to understand a sentence like, "The cat sat on the mat." If you just looked at the words in isolation, you wouldn't know who was sitting on what.
Right. You need to know the order of the words to understand the meaning of the sentence.
Exactly. And that's what positional coding does for transformer models. It provides the model with information about the relative position of each word in the sequence.
So it's like giving the AI a sense of grammar, a way of understanding the structure of language.
That's a good analogy.
Yeah.
And there are different ways to achieve this. Remember we talked about sinusoidal and learned encoding?
Yes, you mentioned that sinusoidal encoding is like a general purpose tool, while learned encoding is more specialized.
Right. Sinusoidal encoding is based on mathematical functions that assign a unique value to each position in the sequence. It's a relatively simple and effective approach that works well in many cases.
And learned encoding.
Learned encoding is more dynamic. It allows the model to learn its own positional embeddings based on the data it's being trained on. This can be particularly beneficial for tasks where the order of words is especially important, like translating poetry or code.
So it's like the model is developing a more nuanced understanding of how word order affects meaning.
Exactly. And that's one of the things that makes transformer models so powerful. They're able to adapt and learn in ways that previous models couldn't.
Welcome back to the Deep Dive, where we're exploring the amazing world of transformer models.
We've covered a lot of ground so far, from the basics of fine-tuning to the mind-bending possibilities of multimodal AI.
And before the break, we were about to delve into multi-head attention. It sounds like something straight out of a sci-fi movie.
Well, it might sound futuristic, but the concept is actually quite intuitive. Imagine you have a team of experts, each with a different area of expertise, analyzing the same piece of text.
Okay, I can picture that. So like one expert might focus on the grammatical structure while another looks at the emotional tone.
Exactly. That's essentially what multi-head attention does. It allows the model to process the text from multiple perspectives simultaneously. Each head focuses on a different aspect of the language, and then they combine their insights to form a more comprehensive understanding.
So it's like having a team of specialized AI working together to crack the code of human language.
That's a great way to put it. And this is one of the things that makes transformer models so powerful. They're able to capture the nuances and complexities of language in a way that previous models just couldn't.
Can you give us a real-world example of how multi-head attention is being used?
Sure, let's say you're building a chatbot for customer service. With multi-head attention, one head might focus on understanding the customer's specific request, another might analyze their emotional state, and yet another might track the overall context of the conversation.
So the chatbot can respond not just to the words themselves, but also to the underlying emotions and intentions behind them. That's pretty impressive.
It is, and this kind of technology is already being used in a variety of applications, from virtual assistants to machine translation to content creation.
This is all incredibly fascinating, but I have to wonder, what does the future hold for transformer models? Where do we go from here?
That's the big question, isn't it? And as you might imagine, researchers are constantly pushing the boundaries of what's possible.
So what are some of the areas that you're most excited about? What's on the horizon for transformer models?
One area that I find particularly interesting is the development of even more sophisticated multimodal models. We're already seeing models that can process text and images together, but imagine models that can seamlessly integrate information from text, images, sounds, and even sensory data.
Wow, that's getting really close to how humans experience the world.
It is, and that opens up a whole new realm of possibilities. Imagine AI that can understand not just what you're saying, but also how you're feeling, what you're seeing, and even what you're smelling.
That's mind-blowing. What kind of applications could that have?
Well, in healthcare, imagine AI that can diagnose illnesses based not just on your symptoms, but also on your facial expressions, your tone of voice, and even the subtle changes in your body chemistry.
That would be revolutionary. What about other fields?
In education, imagine AI tutors that can personalize their teaching methods to your individual learning style, adjusting their pace, their tone, and even the content they present based on your real-time responses.
And in the arts. Imagine AI that can collaborate with human artists to create truly immersive and multi-sensory experiences.
The possibilities are truly endless, and I believe that transformer models will be at the heart of many of these advancements.
So what does all of this mean for the average person? How will these advancements impact our lives in the years to come?
That's a great question. I think it's safe to say that AI will become increasingly integrated into our lives in ways we can't even imagine yet.
Do you think that's something to be excited about or something to be wary of?
I think it's both. AI has the potential to solve some of the world's most pressing problems, from climate change to disease to poverty. But it also has the potential to be misused or even to create new problems that we haven't even thought of yet.
So it's important that we approach AI development with a sense of responsibility and caution.
Absolutely. We need to think carefully about the ethical implications of AI and ensure that these technologies are developed and used in a way that benefits all of humanity.
That's a powerful message to end on. Thank you for joining us on this deep dive into the world of transformer models. It's been fascinating.
It's been my pleasure. Thanks for having me.
And to all our listeners, thanks for tuning in. We hope you learned something new about these incredible transformer models. And until next time, stay curious.